Suppose that x is a discrete random variable that takes on the values 6, 9, 12, 15, and 18. If y is a good approximation for x, determine an expression in terms of y, the probability that x is greater than 9, less than or equal to 15. So we'll get to the probability in a moment, but I find that when you're working with a good approximation, when you're making a switch from discrete random variable to continuous random variable, it's a good idea to draw what I call a mock histogram. Okay? So we want the boxes for this histogram to be written sort of above and centered on the values that x can be. And so x can be, as we see, anything from 6 up to 18, increasing by 3 each time. And so 3 will be the width of our boxes. But we leave it to our imagination to draw the heights. Okay, we'll do a nice, oh, that's a little narrow. Well, we'll make it kind of symmetric, I guess. That's still a little narrow. We'll go over a bit more. That's more histogrammy. Anyway, I'm actually wasting too much of my own time. As long as it's a picture that I understand, then it's fine. Right? Because we're not going to mark you on histograms. It's just a tool to help us visualize this change from discrete to continuous. Okay, so there's my histogram or something similar. It doesn't have to be exactly this picture. What we do need to have is the boxes start where the last one stopped. They need to be centered over the value of x, and we need to remember the area represents probability. Right? Those are the key features of a histogram in this course. Okay. All right, so now what have we got? Well, we want to talk about the probability that x takes a value greater than 9, less than or equal to 15. And the signs here matter because it's a discrete random variable. So would 6 count? Well, no, 6 is less than or equal to 9. 9? Nope, that doesn't satisfy this either. 12? Yeah. 15? Yeah. 18? 18's a little too big. So we couldn't include 9 because x needs to be greater than 9. But we could include 15 because x is less than or equal to 15. Okay. So now I know which values of x I care about. So this probability is represented by this area, the area of these two rectangles. All right. Let's bring in our, what's a good color? Let's use red. Let's bring in our continuous random variable, our good approximation, y. And so remember, continuous random variables use density functions, these nice curves that sort of fit along the histogram. It doesn't have to be exact, okay, but the idea is the area underneath the curve over the same stretch as the boxes you want to talk about is the same probability, roughly. Okay? So we want to talk about the area starting where the blue shaded area starts and stopping where it stops. And so we get this area here. So this red dashed area represents a probability in terms of y, our good approximation. The only question is, well, what range of values for y are we representing? This is why we want to draw our histogram well. Okay? We realize, oh, we start over here halfway between 9 and 12. You can work it out. That's going to be 10.5. And our area stops here halfway between 15 and 18. That's 16.5. So that's the range of values that we want y to be. Y can be any value between 10.5 and 16.5. Of course, you could write it as 21 halves and 33 halves. That's fine as well. Okay? But this is exactly the answer we're looking for. So we draw a pretend histogram that's got the right features. We figure out what boxes to shade in based on the probability in terms of x that we're given. We make a switch for an area under a density function. We figure out where the area starts and stops, and that gives us the range of values for y. That's the general process.